In this video, we're looking at an example to find a whole family of functions, a whole family of series that converge. So we're being asked to find the values of p. P here is the power on this natural log of the natural log of n p's. So we're looking for the values of p so that the series from 3 to infinity of 1 over n, natural log of n, natural log of n raised to the p power is convergent or divergent. Since we're using the integral test here, we'll let our f of x be 1 over x log x quantity raised to the p. Notice that the reason why this series starts at 3 is for a couple of reasons. Certainly we can't plug in 1 here because we'll get a 0 at the denominator. We also don't want to plug in a 2 here because if we plug in a 2 here, natural log of 2 is less than 1 because natural log of e would be 1. If this is less than 1, the natural log of something less than 1 will be negative. And to be able to apply the integral test, we need the function to be positive. So that's why they have us starting at 3 here rather than 2. So the fact that we start at 3 makes this function positive on 3 to infinity. And it's also decreasing because the numerator is constant and the denominator gets larger as x gets larger. Now again, like we mentioned in previous videos, usually the integral test is stated that you want the function to be continuous on 1 to infinity. Really, you just need it to start somewhere. In this case, it starts at 3 that we're looking at. All right. So now we consider the improper integral. Here we'll have u, we'll take our limit of our integral here where we've replaced the limit of the infinite limit of integration of our integrand. We'll need to do a u substitution here, so if we let u equal the inside, our du will be exactly the 1 over x log x. So it turns out we need to integrate the function u to the negative p, evaluated at these endpoints here, and those endpoints are just coming from taking our x values and plugging them in for u. Now, notice that we can take an antiderivative here using a power rule as long as p is not 1. If p is 1, we'll have to do another antiderivative. Antiderivative here is we add 1 to the exponent and divide by that new exponent. So we'll have 1 over 1 minus p, u to the 1 minus p. And here we're going to plug in our endpoints. Now here, the second piece, notice here I've done minus this, but I just went ahead and distributed the minus 1 through the denominator here to make it p minus 1. The second piece here is a number. As long as p is not 1, this is a number. So this isn't going to have any effect on whether or not the limit converges or diverges. We're really interested in the first piece. All right, so in particular for the first piece, we're interested in knowing whether or not this exponent is positive or negative. Because if it's a positive exponent, then this natural log of b ends up being in the numerator of the fraction. If it's negative, then it ends up being in the denominator of the fraction. Okay. So, if it's negative, if p is greater than 1, that'll make this negative. If it's negative, if the p is greater than 1, makes the exponent negative, then we've got natural log of b getting very, very large as b goes to infinity, but it's in the denominator. If it's in the denominator, that whole fraction will go to 0. In which case, if p is greater than 1, we turn out to be that number that we just mentioned before, that 1 over p minus 1 times natural log of 3. If p is less than 1, then this exponent is positive. If the exponent's positive, then this natural log of b gets very, very large in the numerator, which makes the whole fraction get large and makes the integral diverge. So this improper integral converges if p is greater than 1 and diverges if p is less than 1. Now we have one more case to handle. We have the case to handle where p is equal to 1. we need a different antiderivative here. Here's the antiderivative. If it's, here's our substitution and the function we need to integrate if p is equal to 1. Its antiderivative is natural log. Should be of absolute value of u, but everything here is positive, so I can just leave it as a u. Plug in our endpoints here. Now, this is log of log of log of b. Log of b gets very, very large as b gets large, which makes the log log of it get large, which makes the log 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 of it get large. Not quickly, but it goes off to infinity. So the integral also diverges if the p is equal to 1. So the integral converges if p is greater than 1 and diverges if p is less than or equal to 1. So the series does the exact same thing. So in particular, the series converges if p is greater than 1. And that looks a lot like what our p series